So, here what I just go back to this slide, and here what you can see is two resonators as I described last time, and each they are spherical mirrors. So, this is one mirror in blue, this is another mirror, and it has a radius of curvature of R1 and R2. Okay. So, I have put this f is equal to R1 by 2 and f2 is equal to R2 by 2. So, when you put all these things you get this. So, so this is the stability criteria for a laser resonator. Quite often in text and in a lot of literature, they write the stability criteria as G1 and G2. So, I have just introduced G1, G2 should be greater than 0 and should be less than 1, then only the laser is stable, the laser resonator is stable. Now, G1 corresponds to this thing in the bracket, G2 corresponds to this part in the bracket. Okay. So, these are the things. Now, let us see what G1 and G2 does in a resonator. This I have already shown you for matrix multiplication, which you should work out on your own. So, I come to the stability diagram. So, we have the stability criteria, and this stability diagram actually follows the stability criteria of any laser resonator. So, this axis is the G1 axis where all the G1 values are put, and this axis is the G2 axis where all the G2 values are put. And then when you, so there is a curve like this, and when you plot all those points you will get, you can even get a curve of this kind. And everything which falls within the shaded area, it's a bit of a jumbled up shaded area, but anyway anything that falls within this jumbled kind of shaded area is a stable resonator. Anything which falls in this region, this region, this region, this region is an unstable resonator. So, for any resonator that you design, you have to check out for its stability. So, basically you have to calculate G1, you have to calculate G2 and plot it on this diagram and see, does it fall here or does it fall in the shaded area, does it fall here, does it fall in the shaded area, you have to check that out. So, as an example what I take is, suppose the resonator is made out of plane mirrors, okay, absolutely plane mirrors, okay, and the distance between them is d. So, for plane mirrors R1 is infinity, R2 is infinity. You put these values of R1 and R2 into G1, that means you put it here, here, and you see, does it fall between 0 and 1? Okay. So, in case of the planar, once you put it in, it comes in this position, where this round circle is shown. It is just about stable, it just falls on this line, it is just about stable. Okay. And when you are building a laser, you just got to be careful about the distance between the two mirrors. You have got to be careful how you place it. Plane mirror, you assume R1 and R2 is infinity, and it just might become unstable while it is lasing also. So, it is just about falls in the stability part. Okay. Then you have the confocal. What do I mean by confocal? Confocal is R1 and R2 is equal to d. That means the distance between these two curved mirrors, concave mirrors, you have these two concave mirrors and the lasing medium is in between. The distance between them is d, and R1 and R2 is equal to d. Okay. So, the radius of curvature is equal to the distance between the two mirrors, that is called a confocal mirror. Again you put it in the G1 and G2 formula and you come across this point. Okay. This is also stable. It is a stable resonator. Okay. Now, you come to another which is concentric. By concentric I mean R1 is equal to R2 is equal to D by 2. Okay. So, the radius of curvature of these concave mirrors is this distance D, half this distance. Then it is called a concentric resonator. Once you put in all those values, you will find that it falls at just here at the edge. So, it is just about stable and can move into this unstable part if these numbers are not exact. Okay. So, ideally what you would do is you would like everything to fall within this area where you have a little leeway in your alignment system of your laser. Okay. So, for that I have taken another example. This is this. All the resonators need not have plane mirrors, they need not have these kind of concave mirrors. You could have a combination of concave and a plane. Okay. Here R1 is equal to 2D and R2 is equal to infinity. So, R2 is infinity because 1 is a plane mirror. You put in all those values and they fall somewhere in this region. So, it is a pretty much a stable resonator. So, quite often people work with this configuration of a resonator. Okay. Then let us see, we will talk a little bit about the modes. I have already spoken about the longitudinal modes. I describe this again here. Okay, this is delta nu, as I had said, delta nu is equal to C by 2L in that in the previous slides. So, this is a gain medium, again this is the gain profile and this is the threshold or the loss line. So, your modes have to have an energy which falls here. It can cross the loss line or the threshold line, then only it will laze. So, here you can see this mode will laze and this mode will raise and this mode will laze. So, 3 modes can laze. Okay. That means 3 frequencies are possible, but finally maybe only one of them will laze because these 2 will probably get suppressed. Anyway, the idea of showing this is that this is the longitudinal mode. Then there is something called the transverse modes. Actually, there is a big difference between the longitudinal modes and the transverse modes. I have told you the longitudinal modes are frequencies, some kind of frequencies. The transverse modes are actually not frequencies. Okay. They relate to the intensity profile transverse to the axis of the laser. Okay. So, here I have just given you a diagram of the different types of transverse modes. That means these are the spots that you will see at the end of the laser. Okay. And they are transverse to the axis, that is why they are called transverse modes. So, if I have actually this is one axis. So, if I have an axis like this, that means the laser beam is travelling like this, okay, very close to the axis. Okay, here. Okay, I can, this is the axis. The laser beam is travelling along this. Now, this is the beam, this is one. Okay, this is the beam. Now, if I see across this, that means perpendicular to this axis, I will see these kind of spots. Okay. So, these spots are actually actually the intensity distribution. So, you could get a spot which looks like this, you could get a spot which looks like this, this or this, and these are called transverse TEM, okay, these are called TEM modes, and they are not frequencies. Okay, you have got to understand that. Though I have said modes, in case of longitudinal they are frequencies. TEM is a distribution function of the intensity profile. So, the first one is called TEM 00 mode. Here in the picture it is only written as 00. Now, the next one is called TEM 10 mode, okay, and this one is called 20, this one is called 30 mode, and this is 01, 11, TEM 21, TEM 31, and so it goes on. So, all these modes are possible, all these modes that you can see here are possible, okay. And how do I mathematically deduce these modes? It can be deduced very easily, You start off with a Schrodinger's equation, it is a wave equation. Okay, when I spoke about previously, I spoke about ray optics, okay, and not wave optics. But then the lasing medium is the laser itself, the light is a wave, it is a wave. So, it has a wave front and it behaves like a wave. So, we have got to consider that. Okay. So, we can write a Schrodinger's equation, and you can have a wave function which will be a solution to this Schrodinger's equation. Okay. And all these here, all these modes here are actually solution to the Schrodinger's equation that you write. You can derive it very well, it is quite easy to derive. Okay. So, you really want to know how the beam has travelled from one end to the other while passing through the lasing medium or the other kind of optics that is included, whether in a resonator. Here I am speaking specifically of resonator. Within this, what happens to it? Okay. You have to get it to the wave optics. Instead of going through all those the derivation from Schrodinger's equation, you could go through it from the books that have been suggested, and but here I will give you some key points, something that you some formula that you need in order to build a laser quickly. So, one of this is see. So, here this one, this profile is something like an intensity profile. I will not say intensity, I have written E0, that means it is the electric profile. Okay. It is the laser beam has this, it is an electromagnetic wave. So, the electric profile is here, something like this, which goes like this. You can see it is maximum at the center and lesser at the sides. Okay. So, this point is E0, okay. E0 is the maximum. Now, we have a point here which is E0 by E. It is convention to define that, and whatever is the width here, this W, this is between okay, this part is W, okay. W, and sometimes conventionally it is called omega, whatever you might like. Basically, this width has something to do with this intensity profile. Actually, intensity is mod E0 square, or mod E square. So, I have just given the electric field profile, the intensity profile will look similar. So, you will get a width in that intensity. So, I am concentrating mainly on this TM00 mode only, I am not talking about these part. Okay. So, because this is the most conventional and quite often we would like the laser to have a TM00 mode. You know, these have their advantages and disadvantages. So, let us concentrate only on this. Okay. So, here is the electric field or the intensity profile of this TM00 mode. Actually, I have shown it in this axis, but really this is the axis along which the laser beam is travelling, and this is the intensity profile or the electric field profile. It is the same, you just have to make it perpendicular. Okay. So, this is one. Now, what is happening to the laser beam? Suppose this is the laser beam, this is the width of the laser beam, I show it here, omega 0. Omega 0 is the waist of the laser beam. So, this laser beam is coming this way, it comes to a narrow waist and then it diverges out like this. This is the contour of a Gaussian beam, okay, the contour of this and this, okay, and which has a waist omega 0, and this is this width. That means this laser beam between say 2 mirrors, it is going something in this kind. Okay. So, this part and this part, this narrowest part is called the beam waist, which I have shown here W0. Okay. And then this is diverging out. So, if I take a tangent to this, I will get the angle at which it is diverging out, which is theta, and omega or W is the beam size at any point along this axis, call it the z axis. Here I have called it the z axis, it is conventional to call it z axis. And this here is r. R means what is the distance from the axis to some point outside here, r here. R is more here, this is a little more, so it goes. How far it is from the axis, that is r, and that is how you get this sort of a profile. So, now one more thing we need is, we need to know this angle theta, okay, and we need to know the wave front. See this in the dashed line that I have shown, that is the wave front. That means it is a spherical wave front. Wave front means where all the phases are equal along this. So, it is a curved wave front. Okay. You get all these things if you do wave optics, you do not get it if you just do ray optics. Ray optics gives you some idea of the resonator or the beams that are passing through, but to get a complete picture you need to do this wave optics. So, what is the wave optics is giving me the modes, the transverse modes, as well as within the resonator where does the beam become narrowest and what is the value of that narrowed part, and at any other point we want to know what is the width. Okay. So, all these formulas here I have put 1, 2, 3, 4, 5 formulas. These are derived from the wave equation. Okay. So, the most important is this theta, which depends on the lambda is the wavelength of that laser beam, omega 0 is the waist here, and pi. So, I have got an idea of what theta is like. That means I know at what angle the laser beam is expanding and at what point. Then you can get the omega 0 square, that means you want to know the value of omega 0, what is the waist size. That will be given by omega square upon this formula. Everything is known here, radius of r is the radius of curvature, lambda is a wavelength and omega square. So, this will give you the omega 0 waist size. Now, z, I mean z is any point along the axis. So, here is this beam along this axis, any point on this axis, if you know the radius of curvature, if you know that, this is a relationship of the radius of curvature of this wavefront and any point in the axis. Okay. So, this relation is also very important, and then R z is the radius of curvature of this wavefront at any point along z. Everything is known here, omega 0 is known, lambda is known, z is known, everything is known. So, these formulas are interrelated with each other, and they are interrelated in such a way that you can find out what is the beam waist, the way the beam is diverging, and you can make a design of your laser. Okay. So, you design this laser in such a way that you need to take all these parameters into account and you design it. And once you have designed that, you can build any kind of laser with any material in between. So, this will go on, and what I want to tell you is that these modes here, these modes, they give you a very large energy output, you know, as compared to this fundamental mode. TEM00 mode is called the fundamental mode. Okay, and these will give you a larger energy or larger power at the output. Okay, and many of these formula, theta, omega square z, omega 0 square, they all apply to all these transverse modes too. Okay. But there is a problem with these modes. It is giving you larger power, but suppose at the end of the lasing medium you want to focus it to a point, these never get focused, you know. So, most of the time, though your lasing power is a little less, you do not mind having a TEM00 mode. In fact, you would prefer it. Okay. And that is how you make a laser. So, I think you are pretty much equipped to designing a very good laser. Now, we should go on to speak about the different types of lasers that I had introduced to you right at the beginning of this set of lectures. And I would like you to go through some of those, and I will be describing some of them. There is the solid state laser, then there is the gas laser, then the semiconductor laser. Each of them have a different kind of energy level systems. You know, we have seen 3 level, 4 level and all these kind of systems. So, each of them have a specific energy level systems, and you will be able to make a comparison between all of them and see how resonators fit into these different kinds of lasers. Okay.